we're continuing our discussion of polynomial functions. I call this Polynomial Functions Part 2. This still matches with material that's in 5.2 of the textbook. Up to now, we've just been looking at polynomial power functions that have a single term. What we need to start studying are polynomial functions that have several terms and how we can understand their graphs. So in this section, we're first going to look at several examples of cubic functions, polynomials of degree 3. Then we're going to discuss degree 4 and higher degree polynomials. But for now, cubic degree 3. Now we already know that the graph of f of x equals x cubed looks something like so, right? We're real comfortable with that now. If we see minus x cubed, we know we're reflecting through the x-axis, so we get a shape like so. And we also know that we can draw x minus 2 to the third, because what that would mean is I would just shift horizontally to the right by 2 units, so I get a graph looking something like that, and I think this y-intercept is actually going to occur at, if you plug in 0 for x, it's going to be at -8. And so here's what I want to do though. So this is all stuff we already know. I want to multiply this out. So in other words, I can write this function as, instead of x minus 2 in parentheses cubed, I can write it as x minus 2 times x minus 2 times x minus 2. And you can only multiply 2 of these at a time. So I'll multiply x minus 2 times x minus 2 is x squared, minus 2x minus 2x is minus 4x, and then negative 2 times negative 2 is plus 4, times another x minus 2. And now I gotta distribute to multiply here. I'm going to take x times each one of these terms. So I get x cubed minus 4x squared plus 4x. And then I'll take negative 2 times each one of these terms. So negative 2x squared. Negative 2 times negative 4x is plus 8x. Negative 2 times positive 4 is negative 8. And combine like terms. So I have x to the third minus 4 minus 2 is minus 6x squared. And then I got 4x plus 8x plus 12x minus 8. If I write the function in this multiplied out form, this is the same function. Okay. And one of the challenges we're going to face is if we see a function in this kind of multiplied out form, can we recognize the graph? Okay. All right. Now, and we're also going to, the question is, if I see a cubic polynomial with 4 terms like this, or several terms, is the shape of the graph always something sort of like so or not? And so I'm going to switch to try to flip pages here. I guess I wanted to cover that up. So let's ask this question next. After those few examples that we looked at, the question is, do all cubic third-degree polynomials have graphs shaped like this or like that? The 3 examples we've looked at so far in this video each had one of those 2 shapes. And the answer is no. The shapes can get more complicated. And we've actually already seen an example of a cubic, sorry, I'm sliding around too much here. at the beginning of this course, on the graphs and symmetry handout, we graphed y equals x cubed minus 3x. And this is a cubic polynomial function. We didn't call it that at the time, but now we can write it using function notation as f of x equals x cubed minus 3x. And what I want to do is I want to draw this graph again. And I'm not just going to say we already know it because it was a couple weeks ago. And I think it's worth going through these steps again. So we're actually going to just start from a sheet of graph paper here. And let's go ahead. And so we're going to graph together f of x equals x cubed minus 3x. So what are the x-intercepts of this graph? Now to get x-intercepts, you got to take the function expression, and we're going to set the output, or f of x, equal to 0, and solve for x. And I think we did this, right? We back when we could factor out an x times x squared minus 3. We got x equals 0, or x squared minus 3 equals 0. So we got a little quadratic equation we can solve using the square root method. X squared equals 3. So x equals plus or minus the square root of 3. And so we actually got 3 x-intercepts. There are 3 x-intercept points. And let's see, we got 1 is 0, 0. 1 is square root of 3, 0. And the other is negative square root of 3, 0. And I'm trying to think. I think let's just plot a few more points, do a few more calculations for this function, x cubed minus 3x. So I have my x-intercepts, so we got 0, 0, square root of 3, 0, negative square root of 3, 0. If we look for a y-intercept, we're only going to get 0, 0, so that doesn't give us any additional information. I'm just going to plot a few more points, and I'm going to get them by plugging into the expression for the function. I'm going to try to do f of 1 in my head. F of 1 is going to be 1 cubed minus 3 times 1. 1 minus 3 is negative 2. If I plug in negative 1, I'm going to get negative 1 plus 3, or positive 2. If I plug in 2, maybe I'll write out a couple of these. F of 2 is 2 cubed minus 3 times 2 is 8 minus 6, or 2. If I plug in negative 2, I'm going to actually get the opposite of that. I get negative 2. And maybe just for the record, f of 3 is 3 cubed minus 3 times 3 is 27 minus 9 is 18. F of negative 3 is negative 3 cubed minus 3 times negative 3. Just notice the difference now. I get negative 27 plus 9, so I get negative 18. And let's sketch a graph. Oh, couldn't find my ruler. Got it. think I want to spread out a little bit. So I'm going to go 1, 2, 3, negative 1, negative 2, negative 3, and let's see, maybe I'm not so worried about the 3 points. I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 10. All right, I'm not going to be able to fit my negative 3 point, but that's okay. It will be good enough. So there's 0, 0. Square root of 3 is, we can estimate with a decimal, that's about 1.7. So 1.567 is about here. Negative 1.7 is about here. So there are my 3x intercepts. And we got 1, negative 2, which is 2, 4, 6, 8, 10. So that's right here. And we got negative 1, positive 2 right here on this scale, right? Because that's 2. That's negative 2 for the scale I set up on the y-axis. And 2, 2, 2, 2. And negative 2, negative 2. And then I got 3, 18, way the heck up there. And negative 3, negative 18. I'm just going to exaggerate that a little bit because I barely fit it on. So what I'm just trying to remind us of is we got a graph that looks something like so. Okay? And so that's a more complicated kind of third degree polynomial graph. Notice how we have this wiggle to it. So let's maybe just write the function name next to this graph. That was x to the third minus 3x. That was actually third degree polynomial with only 2 terms. So, so notice the wiggle. And by that I just mean this sort of twisting through the middle. And also note that the end behavior matches f of x equals x cubed. And we're going to see that it turns out this leading term is going to have a lot to say about what the end behavior of the function is. Okay, so after that example, just to wrap up where we're at right now, it turns out that these are the possible shapes for a cubic degree 3 polynomial function. So we kind of have this x cubed kind of squiggle. We have the wiggle going up, down, up, like we just saw in the graph we just completed. Then we kind of have the minus x cubed. And we're going to see you can also have like a down, up, down wiggle. We haven't seen an example of that yet. So what kind of shape is not possible? We won't be able to go like up, down, again. This has too many wiggles. So we're gonna learn. I mean, right now I haven't really defined wiggle, but this kind of shape is not possible for degree 3 polynomials. And I think I'm going to wait for the next video where I see the example down there at the bottom. We're going to graph a degree 4 polynomial in the next video segment.